Does anybody have homework questions to go over? Your quiz is on Wednesday. There's a special study group tonight for the quiz. Okay, so from 1 to 2 in Wood Hall 202. So actually it's this afternoon, not tonight. Now if you can't make that for some reason, you can contact the tutors by going to www.uwgb.edu/tutoring and try and set up a different time to meet with them, okay? And you're welcome to stop by my office as well. We were looking at the Mobius band, this interesting band that we made in class on Wednesday. There are applications of the Mobius band. This is an article from Wikipedia. So you've seen Mobius scarves, but there's also things like continuous loop recording tapes or Mobius resistors or compact resonator with a resonance frequency that is half that of identically constructed linear coils, or inductionless resistors, superconductors, a Mobius resonator. Some other applications include molecular knots with special characteristics, molecular engines, a graphene volume with new electronic characteristics. I wondered what this is, a special type of aromaticity. That's what the way things smell, right? How would a Mobius band make things different in smelling? We also have these other applications as well. So the Mobius band does have applications beyond that. It's kind of interesting and quirky. Also, I brought a model of a Klein bottle in 3 dimensions. Remember, we made the Mobius, we made a tube, and we wanted the tube to connect in a way that it had no edges and just one side. And here's a 3-dimensional representation of a Klein bottle that has that characteristic to it. So I'll pass this around the room. Can you please pass this along? Thank you. So we'll be looking at the reviews today for quiz 2. So we had the review from chapter 3.1. That was back on the first review. So hopefully you saved that from your printout there. And I remind you to print that out here as well. So this is the review for chapter 2, for quiz 2. You might, well, for sure I think you should bring a 3x5 card. You might want to bring Pythagorean right triangles in a square if you like to construct a physical Pythagorean proof. For sure bring a compass. Okay, a compass like this to sketch. And for sure bring a ruler so that you can make some measurements. You might want to bring your platonic solids. You might want to bring tape and scissors. So the quiz has about 39 problems. 31 are on the Scantron, so multiple choice. The rest are short, or some are kind of long answers. The material covered is from 3.1 to 6.2. But not 4.7. So we'll go on our review here and cross off 4.7 in a minute. Well, I don't know that we want to cross it off. It's for quiz 3, so you could use the, save the sheet for quiz 3 like you saved the other sheet from quiz 1. So 4.7 is for quiz 3. Also, I didn't want your 3x5 card to be all taken up with this chart. So you can cross off these two columns, just keep the number of vertices, number of edges, and number of faces, and those are what I asked you questions on the quiz. We're going to split up into groups and work on this. Does anybody have any questions before we split up into groups? Okay, so we'll need groups of 2 or 3 to work together, and then we'll work for a few minutes and then fill in this sheet together. So I'll come around and assign you a section, okay? Do you want to turn around and work with the person behind you, please? And you can have section 3.1. Okay. Do you two, well, actually, do you 3 mind working for you? So you can do 3.2, please. And then can you 2 please do 3.3 together? And this is good. You can either do 3.4, which is the one you emailed me about.
Oh, okay.
I need a group to do 5.2. Does anyone have kind of a short section and not mind doing 5.2? Yes. So your group is going to do 5.2. Got it. Okay. If you're stuck, raise your hand. So what is your group?
Oh, it's 1.
You're not sure if you're in 4.2. Oh, okay. What is your group?
It's gas and one side and one end.
So you go online and look at it. Well, that's the one. Do you have access to the timeline? By the class, yeah. So I think, okay, and then, and I think it's under the read study practice. So if we go to the bottom of section 3.1, then you can actually look at the read study. So this one, do you remember what we had this for in class?
We have.
That's what I'll do. Do you have an example of classroom of two sets that one time about what
Like Dave, you're one.
Yeah, that would be
Because I had to send it to her.
But, and then is that all we need for this one?
I think so. What are the Mindscapes 13 and 20? So when you see what those are, then we'll see. Okay. I think they're more examples of one-to-one sets.
Unprovable because they've proven that there's no way to prove this, and they've also proven that there's no way to disprove it.
Now, she's looking for more than just, you know, is she just
So I can see. No, I think also.
Oh.
This one, I'm like.
I feel like somewhere there should be a question of putting two infinite sets into one-to-one correspondence.
Which one?
Oh yeah, I think that's in the Mindscape 14.
Yeah. You know what I'm saying?
No.
Yeah.
That's my.
You might go through some of the things.
Yeah, I have the right side for your order. I have a ruler. You don't have one. Oh, so we have to get it. So we have to bring all that stuff to quiz in order to take it.
Okay, so is that
No,
right?
that's just some stuff you might want. But for sure, bring a ruler and
And a compass.
and your 3x5 card.
Where can we get it? So that they can like out at the resource.
You can
borrow it. Thanks. Wait, ruler. She didn't say something. I'm sorry. I have a ruler too, so like, we're not like.
Okay.
What is that? You have the softball team first. I've improved to have more eyes from your name. You have the
That looks super nice. It's a question saying, is there a one-to-one correspondence between those residents and their social security numbers? And the answer is no. So like, there's 100 So I'm looking for the Mindscapes and there, there's like.
So go under read, study, and practice. And then we're going to look at that in class.
So we don't need to worry about that one? We'll just do it together in class? Like right now?
Yeah.
Okay.
Let's work together for a bit. Some of the review refers to Mindscapes in your textbook. So let me show you how to find those. To find your mindscapes, you would go to Read, Study, Practice, and under Read, Study, Practice, pick the section. So for example, section 3.1 is after the chapter opener, beyond numbers, what does infinity mean? That would be the 3.1. Then page down to the end of the section, and you'll see the mindscapes. So 3.1 on your review says, understand that two sets can be the same size if and only if their elements can be put into a one-to-one correspondence, and then there's mindscapes 13 and 20. So number 13, is there a one-to-one correspondent between U.S. residents and their Social Security numbers? Explain why or why not. Did you get a chance to look at that question at all?
I know the answer's no.
The answer is no. Does anyone know why there's not a one-to-one correspondence between U.S. residents and their Social Security numbers? Because well, everybody doesn't get a Social Security number,
Yeah.
right? There's people who are visiting on visas, for example.
Oh, because those residents and not citizens.
Yes, because they're residents and not citizens.
So,
Yeah.
is it a one-to-one correspondence for U.S. citizens?
I would still say it's no, because at any given moment, there's a lot of babies being born who have not yet gotten their Social Security number. So even if it said citizens, I think it would still say no.
When do you get your Social Security number?
I don't know. I think usually parents apply for it while the child's in the hospital being born yet.
Oh, I thought it was just like after.
The IRS is standing there when you're born waiting to collect your taxes, right? No, I'm just kidding. Let's go back to our review then. What is a one-to-one correspondence? Do you have that? An answer for that?
We just have the definition that two sets are the same size, only if their elements can be put into a one-to-one pairing.
Okay, a one-to-one pairing. So that that one-to-one pairing is where you have every element is used. One time. None are missed. None are used twice.
Can you give us an example of that?
Sure. So we have a finite example that your group came up with. What was an example of a finite one-to-one correspondence?
A, B, C, D, E, 1, 2, 3, 4, 5.
So A, B, C, D, E, 1, 2, 3, 4, 5. Because you can take this set we'll call A, and this set we'll call B. So the arrows are indicating which element goes with which. A goes with 1, B goes with 2, C goes with 3, D goes with 4. None are used twice, none are missed. So that brings us to 3.2.
I have another question.
What's that?
Can you give us an example of what wouldn't be?
Sure. So these are both one-to-one. There's a one-to-one pairing, so these are the same size sets. Does anybody have an example of one that would not be one-to-one?
Could you just move the numbers down? So A to 2, B to 3. And then it wouldn't be 1 anymore.
It'd still be one-to-one because when you got to E, you could go back and put it with 1. What would be an example?
Would you do like 1, 2, 3, 4, 5, 6, and then A, B, C, D, E?
Yes, that would be an example of a set that there is not a one-to-one correspondence. Because one set has one more. There's 6 numbers and only 5 letters, so you're not going to be able to pair them up. Okay, good. Any other questions? So with finite sets, you can count what you have. We're going into 3.2 next, where you have infinite sets. Do the set of natural numbers and the set of rational numbers. Okay, natural numbers are all the counting numbers, so that's an infinite set. Rational numbers were the set of fractions. So we show that with the ratio A divided by B, where A and B are integers. And did that, you had 3.2, what did you decide? Is that the same cardinality? Yes. Yes. Even though it doesn't look like it at first glance, we were able to make that spiraling one-to-one correspondence that connected every element exactly once. So in Mindscape 6 through 10, you had some other infinite sets to set to make a one-to-one correspondence with. Did you get an example to look at those at all? Did you get a chance to look at those? No?
So I didn't repeat it?
Yeah, so these kinds of things, you had the set of natural numbers and then multiples of 3, for example. So both infinite sets whoops, I accidentally put it on the wrong line. How would we demonstrate a one-to-one correspondence between these two sets? Do you remember? What would you do?
Pair 1 to 3, 2 to 6, 3 to 9, 4 to 12, and then it would go on forever.
Good. So show the pairing 1 to 3, 2 to 6, 3 to 9, and as you said, it should go on forever. So make sure you put dot, dot, dots, and make your double arrows to show what goes with what. And you can see here, none of either set are missed. Okay, all the multiples of 3 are represented, and all the natural numbers. Yes.
So like I could like pair like 4 with 9, 4 with 15.
So right, 4 couldn't be paired with 9 and also with 15. One element from one set with one element in the other.
But say like 3 was paired with 15 and 4 was paired with 9 and 5 was paired with 3. Like,
so
there
are other ways to draw your arrows. Just make sure that you have a pattern established so that every single element's used, none are missed, okay? And none are used twice.
So it doesn't have to go in that way.
It does not have to go in this way, but it's probably the easiest way. Any other questions? Okay, so the actual question in 3.3, do the set of natural numbers and the set of real numbers have the same cardinality? What did 3.3 decide? Is that, who had 3.3? Yes, okay, what did you decide?
The cardinality of the real numbers is larger than the cardinality of natural numbers.
Good. So the answer is no. The cardinality of the real numbers is larger than the cardinality of the natural numbers. So we looked at the natural numbers, which are the counting numbers, and for a long time it seemed like all the infinite sets we saw could be put into a one-to-one correspondence with the natural numbers until we came to the real numbers, which are all the numbers on the number line.
So like even the fractions?
Even the fractions, those are the rational numbers, but also numbers that are irrational, like square root of 2, square root of 5, pi, all the numbers on the number line. The proof that we had for that was Cantor's diagonalization proof.
So negative numbers aren't natural numbers, right?
Negative numbers are not the natural numbers, correct? So we had Cantor's diagonalization proof that found that missing number. So let's see if I put the chart up for you, if it brings it to mind. If you remember, I showed you several charts along this line, and we came up with a missing number that was not on this chart by looking at the dodgeball method. We looked at the first decimal place and made sure that was different for the first number. The second decimal place we made sure was different for the second number. Third decimal place we made sure was different for the third number, and so on. So there are some practice problems for those. They're Mindscapes 7 through 9 and 12. And because these are good for you to practice and you don't have the answers necessarily, I put the answers on Canvas. So the answers for these are on Canvas by the review. So this takes practice and it's worth more points. Everything that takes practice in this class is worth more points. So I suggest that you practice these and check your answers on Canvas. They're posted next to the review, right below the 3 reviews. If we have time, we can come back and look at one, okay. Any other questions before we go to the next section? Okay, so we're all about different sizes of infinity. The real numbers were the first size of infinity we found that were larger than the natural numbers. That brings us to 4 questions in 3.4. The first question, is there an infinity that is greater than the infinity of the set of natural numbers, yet less than the larger infinity of the set of real numbers? Okay, so we have these 2 sizes of infinity going on, the size of the natural numbers and the size of the real numbers. Is there infinity in between there is what we're asking. What did your group say?
Unprovable.
Unprovable, very good. That's exactly what the continuum hypothesis says. So the continuum hypothesis, another question in here. There it is in green. There is no cardinality between the cardinality of the set of natural numbers and the cardinality of the set of real numbers. But it's a hypothesis. And then we see that Kirk-Odell proved that's impossible to disprove, and it's impossible to prove. You don't have to be able to quote the continuum hypothesis. So I didn't want you to try and squeeze that on your card. Okay, so that continuum hypothesis is something for you to understand, that it's unprovable whether there's another size infinity in between the size of the natural numbers and the size of all the numbers on the number line, all the numbers that you know that don't have an I. Okay, well, we only got to the first question and then I got off. That's what teachers do. All right. What was question 2? Is there an infinity greater than the infinity of the set of real numbers?
Yes.
Yes. Yes, there is. Did you have an example for that? Did you remember it by chance?
Well,
Anybody?
we got a little help, but it's the
Power set?
power sets, yes.
Yep, the power set of the real numbers. So that's what we did in 3.4. We made power sets of sets. So we'll look at that in a minute. Okay, so yes, there is an infinity greater than the infinity of the set of real numbers. Number 3, are there infinitely many different sizes of infinity?
Yes.
Yes, there are infinitely many sizes of infinity, because you can make a power set of the real numbers, then you can make a power set of the power set of the real numbers, and then a power set of the power set of the power set, and so on. So you can keep making different sizes of infinity in that fashion. Is there a largest infinity, one that encompasses all others? No. I see your head shaking. No, that's correct. There is not a largest infinity, one that encompasses all others. That leads to kind of a paradoxical question, like can God make it so there's no God? You know, it's like, wait. it's a paradox. You can't have that. Okay. It just doesn't make sense. So there's no largest infinity, one that encompasses all other. There is not. So a power set is when you start with a set. So we'll say the set of the numbers 1 and 2. And then the power set was all the subsets of the set. So the power set of A, if A is just the numbers 1 and 2, the power set of A is all the subsets of A I can make. So the number 1 would be a set. So it's the set of all the sets I can make out of A. So I can make the set with 1 in it, the set with 2 in it, the set that's empty. I can make the set with the number 1 and 2. So a power set is a set of sets, including the whole set and the empty set. Well, Cantor's power set is in your book in green here. For any set S, finite or infinite, the cardinality of the power set of S is strictly greater than the cardinality of S. So that's how we keep making bigger size sets. We make a power set of the real numbers that makes a bigger set than the real numbers. We make a power set of the power set of the real numbers, and that makes another bigger set than the power set of the real numbers. This is not something you have to know. It's not to quote, okay? Just to understand. To understand that their power set is bigger than the set that it came from. Any questions? That brings us to 4.1. We had 3 proofs of the Pythagorean theorem, so the 4.1 group is going to lend me their proofs. Is that your group? We looked at 3 proofs of the Pythagorean theorem. You only have to know 1. So there were 3 proofs that I refer you to that section on the video because we won't have time to go over these again today. But the first proof had 2 diagrams plus the algebra that goes with them. For all the proofs, your diagrams have to be nicely labeled, which these are beautifully labeled, okay? You have right triangles, your sides A, B, and C are labeled. The second proof had 1 diagram, and then it had more algebra than any of the other proofs. The third proof had the least amount of algebra, but it had 2 diagrams. So the 2 diagrams showed the same figures used to make c squared as made a square a squared and a square b squared. So c squared equaled a squared and b squared, and you have to clearly identify all the parts on your triangles there as well as the a squared and b squared. That's to show the same shapes made both c squared and a squared and b squared, so they are equal. So everybody should know the Pythagorean theorem because you'll need to use it to be able to find the length of the side of a right triangle given two sides. So that is something you'll be expected to be able to do. And we practiced that in class, so you could go ahead and review that whole section. So again, a lot of points in these 4.1 problems. Anything that takes practice is worth more points. That brings us to section 4.2. Here, I'll give you the whole class several curves, and you can decide if they're polygonal closed curves or not. Okay, so I'll label these A, B, C, and D. You decide which ones are polygonal closed curves. At your desk, please. So 4.2, what do you think? Well, people are still drawing. Never mind. Wait a minute. Okay, 4.2 group. What?
A and B.
Yes, A and B. A and B are polygonal closed curves. Then the arc gallery theorem is quite long, so I'll put it on the screen. 4.2. Again, this is something to use, not to quote. So you don't need to write it on your card unless for you that helps you to use it. The arc gallery theorem. Suppose we have a polygonal closed curve in the plane with V vertices. Then there are V divided by 3 vertices from which it is possible to view every point on the interior of the curve. If V divided by 3 is not an integer, then the largest number of vertices we need is the biggest integer less than V divided by 3. You can demonstrate that you can use this by being able to triangulate a polygonal closed curve. And again, this takes practice, so it's worth more points. I'll make a polygonal closed curve here. And we will go ahead and show how we can demonstrate our understanding of the arc gallery theory. We'll triangulate it, color the corners correctly, and choose the placement with the least number of security guards. And we're doing this all the way the arc gallery theorem says. So we're not just doing it using our intuition. We're following the arc gallery theorem. Remember, as you triangulate, you're connecting only vertices, corners only, and no crossed lines as you connect. There is more than one way to do this. So if you're doing this a little differently, there is more than one way, but you should have all triangles, no crossed lines, and you should only be connecting to corners, or otherwise known as vertices. Use a straight edge when you do this, please. You can write down how many red, white, and blue vertices you get, and even if you make your triangles the same as me, you'll still not necessarily put the red, white, and blue the same place. However, I will check and make sure you shouldn't have 2 reds on one triangle. You shouldn't have 2 blues on one triangle or 2 whites on one triangle. Every triangle should have red, white, and blue, and that's it, not 2 of one color. So that does take a little practice. How many vertices do we have anyway? 1, 2, 3, 4, 5, 6. There's 7, so I should come out to 7 total here. We have 3 red, 2 white, 2 blue. So the arc-gallery theorem says I'd need at most 7 divided by 3, or this comes out to 2.3. So at most 2. And in fact, we do see that we need at most 2. Either you can pick the white corners or the blue corners. I'm going to just pick white.
So we have to divide by 3 every time?
You don't have to show you're dividing by 3. That would just be to check. You do have to show this.
So why did you divide by 3?
I'm showing you that the arc-gallery theorem is saying that the most we need is 2. And look at that, the most we needed was 2.
I'm just really confused by the 3.
So the arc-gallery theorem says if you have 7 vertices, which this one had, then there are 7 divided by 3 vertices, which is 2.3. 2.3 vertices from which it's possible to view every point on the interior of the curve. But 2.3 is not an integer, so the largest number we need is 2.
So let's say that it was 2.3 was if you did 7 divided by 3, like say that was the answer, then it would still be 2 because it's the small, it's less than but still an answer.
Exactly. The biggest integer you can get that's smaller than 2.3, the biggest whole number. Any other questions? That brings us to 4.3. So in 4.3, we're looking at the golden rectangle. Remember, that was the one that shows up frequently in art because it does seem to appeal to people. So I will give you a number of rectangles like you see here and ask you to find the one that has the that is closest to being a golden rectangle. So that's why you'll need a ruler, so you can measure and take the long side length divided by the short side. And what do you want to get close to? Good, 1.6. Yep, 1.6. So that was about what phi is. So if you get between 1.5 and 1.7, be satisfied, okay? All right. So, yeah. So I'd like to show the 2 golden rectangles that we learned to sketch in class. Who had those in 4.3? Okay. Bring those over here. You learned to sketch a golden rectangle 2 different ways, and I will ask you to do those. And again, those take practice, so they'll be worth more points. See how we have a square here to start, and then in the square we measure from the middle bottom to the upper right, and use a compass to draw that measurement down to get how wide your golden rectangle should be. So thank you for sharing that. And then we have the other one. This one was made of squares following the Fibonacci sequence. So you have 1, 1, 2, 3, 5, 8, 13 for the Fibonacci sequence. And we follow that by squares. 1 by 1, 1 by 1, 2 by 2, 3 by 3, 5 by 5, 8 by 8, 13 by 13. And then we draw the golden spiraling through that. And there will be a little bit of graph paper on your quiz so you can draw this nicely. When I'm correcting these, the errors I see most are not using squares. You need a square to start, the one with the compass, and as you're building the logarithmic spiral one, using the Fibonacci sequence, those should all be squares. Make sure you're using squares. We went over that in the video very carefully, so you can certainly double check there if you need to. That brings us to 4.4, where we're looking at symmetry. So in 4.4, you'll need to take a figure and decide if it has symmetry of scale or symmetry or rigid symmetry. Or both, right? Because we could have both. So you'll be given a figure. Here's one with squares. Now, who's in the 4.4 group? Okay, good. If I wanted to describe symmetry of scale here, how could I demonstrate symmetry of scale?
Take 4 of the squares and then make a super tile.
Good. Take 4 of the squares and put them together to make a bigger square, which is called a super tile. So if you group these in sets of 4, you still get squares grouped in the same pattern as when there were separate little tiles instead of groups of 4. Then that's described as symmetry of scale, and I have that underlined here for you to see. The pattern in the plane has a symmetry of scale or is scalable if the tiles that make up the pattern can be grouped into super tiles that still cover the plane, and if scaled down, can be rigidly moved to coincide with the original pattern. So you don't have to quote that, you have to be able to know it to use it, okay, not to quote. Well, if that helps you to use it, then you can quote it, but your 3x5 card is only 3x5. So here we have an example of rigid symmetry. Rigid symmetry we did with transparencies, right? So the rigid symmetries, if you could slide your transparency or rotate it or flip it and still land on top of the original shape, that was called rigid symmetry. So you'll need to know the difference so that you can use the correct words when you need to. So a rigid symmetry of a pattern in the plane is a motion of the plane that preserves the pattern and does not shrink, stretch, or otherwise distort the plane. So again, you need to be able to know that definition to use, not to quote. Also, you'll have to find a super tile in the pinwheel pattern. The pinwheel pattern can be printed off the Canvas homepage under class activity materials. So it's just this diagram, and you'll have to be able to find 5 groups of 5 making a super tile. Remember, that wasn't the easiest thing. So again, you have to practice. If you have to practice, it's worth more points. So I encourage you to print this off and practice finding a super tile. It'll be the same drawing on the quiz, the same diagram. Your groups, you're all doing so well here. Thank you for all the work you've been putting together that we're putting all together now. So let's look at 4.5. Who had 4.5? Who did? Okay. I'm going to ask you to help me fill in the chart. But I'm going to just double check, so I'm going to find what I wrote down too. So, for the tetrahedron, how many vertices, edges, and faces?
4, 6, 4.
Okay, 4, 6, 4. Good. For the cube, vertices, edges, and faces?
8, 12, 6.
8, 12, 6. How about the octahedron?
6, 12, 8.
6, 12, 8. Good. And how about the dodecahedron?
20, 30, 12.
20, 30, 12. And the icosahedron?
12, 30, 20.
12, 30, 20. Thank you. Now, I always try to get everybody in the group working, so how about, can you help me with the duality?
Yeah.
What's it?
Octahedron and cube.
Okay. Octahedron and cube are dual?
The icosahedron and the dodecahedron.
Okay, good. Icosahedron and dodecahedron are dual. And you see that in their numbers, right? How their numbers are like transposed? Okay, good.
And the last one's dual with itself.
Good. The tetrahedron is dual with itself. Okay, so you will need to know those.
Can you go back for a second?
And then for 5.2, can you turn to your notes and we'll fill the 5.2 one in together? Oh wait, no, you did do 5.2, didn't you?
Yeah.
Okay, good. So the identification diagram, what's the first one right here?
They said it was just like a normal loop.
Yep, a plain loop. Also called a cylinder. How about this one?
The Mobius band.
Good. So the Mobius band has the opposite arrows because we had to twist them. We put a half twist in to get that those arrows to line up. What about this shape?
That was the torus.
Torus, good. Shaped like a donut or inner tube.
That was a cylinder.
Yep, this one's a cylinder also. Just shaped more like a long tube than the first one.
And the last one was a Klein bottle.
Good. The last one's the Klein bottle. So it has the opposite arrows too that need to be twisted to fit together. How many sides does a Mobius band have?
One side.
One side? How many edges?
One edge.
One edge. Good. So the last section you can make sure you have V minus E plus F equals 2 on your card so that you can use that. The Euler characteristic of connected graphs. And you can go ahead and try the one at the bottom of the page there, or kind of toward the middle there. So everybody in class, count how many vertices, edges, and faces that has, please. If you get done, then you check it by using the Euler characteristic of a connected graph. So the vertices are the beginning and ending, and then wherever the graph crosses itself. So this one has 5 vertices. The edges are in between points, so you can follow along. 1, 2, 3, 4, 5, 6, 7. And faces are enclosed, and the outside counts as a face. So I will also give you a problem where I give you 2 of the quantities. That's what, I can't remember if Mindscape 15 is this type of problem or where I give you 2 of the quantities and find the third. So we have an example of that in our video. If you have any questions, see me after class. Or if you want to stay, I'll work one of these out real quick at the end, okay? So if there's 20 vertices and 8 faces, how many edges? If there's 20 vertices and 8 faces, fill in here. E minus E plus F is 2. 20 minus E plus 8 is 2. You can add the 20 and the 8. They're both positive. So 28 minus the edges is 2. You have to have 26 edges taken away from 28 to leave 2. So edges is 26.